Okay. So go ahead and just like, that'll be your last trial. Okay. All right. So what are you noticing about your data from your Skittles lab?
It goes up fast.
It goes up fast. So when you have your dots, does it kind of look like this? That's not my pen.
Yeah.
Okay. It's way steeper. Okay. Why do you think that is?
The increased amount of Skittles means there's an increased amount of chance for Skittles to not land with the S this one.
Okay, so what is the chance of you rolling a Skittle and it landing with? It's 50-50, right? Oh, there was just no S on it at all. Should have seen that one. Okay. There's always a little bit of room for error, right? So every time you're expecting maybe half of your Skittles to have new friends, right? Okay, now I didn't have you do this because we seem to take a little bit of time to get going. But what if we started with 80 Skittles? Let's just pretend we started with 80. But instead of adding, we take away.
It would go down really quick.
It would go down really quick like this.
Yeah.
Okay, so we have dealt with one kind of graph, linear graph. Obviously, these are not linear. Do you know what kind of model this is?
Skittles. Curve.
That's the best you can give me?
No, it's a curve.
Okay, so what words did you use to describe? So Connor says that the numbers were massively increasing. What other descriptive words did you use?
Curve.
Ooh, a growth. Okay, I like it. Okay, you can go back to your seat, Jacob, and I'll have you turn to page 180.
Oh, okay.
The function that we just modeled is an exponential function. Kind of crazy because guess what we've been talking about? We've been talking about exponents. 180.
I need to find my book, by the way.
Oh, I knew it would turn up.
You know exactly where it was? You want to guess? You want to guess where it was or something?
Where?
I think you can take a slight gander and find exactly where it was. In my backpack, the entire
I told you.
I told you. Trading
All right.
blues for greens. Trading blues for greens.
So hey, I really need you to be focused up here. Okay? Here we go. An exponential function is going to look like this. Hey, this is what our Skittles look like when the number being raised to the power is bigger than 1. Okay? This is what we call exponential growth. Okay. Our Skittles were growing exponentially. Lucky for you, right?
Yeah.
All of them at one time.
Do it.
No, please don't do that. That was not a dare.
Oh,
Okay.
no, 20 bucks.
Now,
You got to get them.
this right here is called exponential, not growth, but, ooh, I like it, but we're going to call it exponential decay. Okay, we're just going to go a little simpler with our word. Okay, and this happens when the number raised to the power is smaller than 1. So it's like 1/2 or 2/3 or something like that. So it does say that B needs to be positive. Okay, what?
He's trying to steal my Skittles.
All right, so now this is what I want you to write down. So back in chapters, whatever we did before Christmas, we talked about linear functions. And linear functions, what did their graphs make? Linear functions were lines. What was true about linear functions? What did they, what? Ooh, and what do we call that? Are you okay? Okay. She's good. She's good. Okay. Linear functions have slope. They have a constant rate of change. Okay. So you remember if we looked at an XY table, our Y's would be increasing or decreasing by the same amount. All the Y's were plus 2, plus 2, plus 2, plus 2, or maybe minus 3, minus 3, minus 3, minus 3. Okay. However, when we have an exponential function, okay, whether it's growth or decay, okay, what is happening is Y is being multiplied by a constant factor. Okay, so what was happening is basically every time you rolled your Skittles, you basically like added half of it. I mean, not exactly. So roughly from term to term, your Y's sort of were being multiplied by 1.5. Okay. You started out with 1 Skittle, then maybe you had 2 Skittles, and then maybe you had 4 Skittles, and then maybe you had 6 Skittles, and then maybe you had 9 Skittles. Okay, something sort of like that. Yeah.
It wasn't like the exact same.
So it wasn't, and that's the thing. When we did our Skittles, it was approximately exponential, okay? It's not going to be exact because we're working with some random chance here. But it can be modeled exponentially, okay? So what I want you to do is I want you to look at the next page, okay? And our goal is to be able to tell, hey, do we have an exponential function or do we not? Okay, do we have a linear function? Okay, so do you notice, this is first, do you notice how our x's increase by the same amount on both sides, all the way down? Okay, so that's good. We know that there is some pattern here. Now, what do you notice about the y's? Are we adding or subtracting the same number? Or are we multiplying by the same number? Okay, so what are we dividing by?
2.
Which is the same as multiplying by 1/2. Okay, so from 8 to 4, we're multiplying by 1/2. From 4 to 2, we're multiplying by 1/2. From 2 to 1, we're multiplying by 1/2. So since our y values are multiplying by the same number, this is an exponential function. Specifically, exponential decay. Use your brain, people. Are our numbers getting bigger or smaller? Okay. And the number we're multiplying by over and over is smaller than 1. That's how we know it's decay. Okay. Now, look at this example number 2. First of all, we have our x values going up by 1 every time. So we have that pattern. But what is our pattern over here with our y values? Adding 4, is that right? Okay, so Ellery, would this be exponential or linear? Yes, this is a linear function. We have a constant rate of change of 4/1, okay? Our y's are adding the same number, could be subtracting too, okay? This is a linear function. How about you take 30 seconds and decide what number 3 and 4 would be?
Pretty simply like that. I'm thinking exponential. Exponential. No matter. The difference between 8 it's not exponential. It's exponential. Exactly. Yeah, here's the constant rate of change. Exponential is when it like. So how is it up? Huh? I thought it was
Exponential.
yeah, that's what I'm saying. With rate being linear.
Yes.
How? Just go on this one. Tell me because it's -3 for them.
Isn't it -3, -3,
Yeah,
-3?
but like, well, that one's going down. That one's going up. So that one.
Well, but this was multiply by 1/2, multiply by 1/2, multiply by 1/2. It's not about going down or up. It's about how it's going down. All right, here we go. Gabe, is number 3 linear or exponential?
I'm still not sure.
Okay, so what do you notice about the y values? They're going down. So -3, -3, -3. Right? So yes. Number 3 has a constant rate of change. Okay. Now, what do you notice about number 4, Kyron? We are multiplying by 4 from y value to y value. So this is exponential. Yes. And this would be exponential growth because we're multiplying by a number bigger than 1. Okay. Okay. Now let's go down here. I want you to make sure that you can do this. Oh my goodness, people. Hey.
What the heck? What the heck?
Deep breath. X is 5. So you know what I'm going to do? I'm going to write y equals 3 to the x is 5. So I'm going to replace x with 5.
Finish. I know.
243. It's basically 81 times 3. So yeah. Guys, it is not time to go yet. It's 21. How about this one? Y equals 1/4 cubed. Hey, what's 1 cubed?
3.
1.
1. What's 4 cubed?
12.
64.
64. Did we all like forget about exponents? 1 cubed means 1 times 1 times 1. 4 cubed means 4 times 4 times 4. Hey, what about this one? We have to do 4 to the 4th first before we can multiply it by 3. Please do the exponents before the multiplication. Okay?
700. 68. 768.
Yeah, 768.
In my head. My word.
Okay, I promise to post the homework before 3:10. I'm sorry. Sorry.
I did so bad.